So if I plot it, it will be like this, no? So if this, for example, was time, no, then your overall signal, fancy V, capital N, no, would be made up of your large signal, so capital V, capital N, plus the small signal, which is the small v, small n, no? All right. So that's what a small signal is. Why are we interested in small signals? Well, small signals, because they're small, are candidates for amplification, no? And this is how we analyze amplifiers, no? So for example, for a common emitter amplifier, you remember ganito yung itsura nung voltage transfer curve niya, no? The output of the amplifier is this. The input of the amplifier is this, no? So if we bias it at a specific V in, no? The quiescent V in that we choose and the quiescent V out, no? That we choose, then yun yung middle, no? That's the quiescent point, right? And this is what midterms will be about, no? Trying to find what the quiescent point is, no? So, then if we apply a small signal, no? That's your small v, small n, no? You find that, well, sige. You know, if you apply a small signal, small v, small n, you find that it comes out, no? As another small signal, but it's not so small anymore. It's been amplified, no? And in fact, what happens is that we now have this graph, no? Now, straight lines, the bane of my existence. So against time, no? V out is now like this, no? It's centered here, no? But now, it has a small signal around it, no? So this is V out. Small v, small out. No, it's the small signal portion of V out, no? It has amplified the small signal part of V in. And that's what we use amplifiers for, no? So, yeah, that's the entire concept of what we're doing, no? So, also, we know how to analyze large signal circuits, no? So, it's the process of analysis, right? We know how to analyze the large signal circuits. Well, okay. We know how to analyze the circuits in DC, no? We know how to analyze them in large signal form, no? So this circuit, we know how to crunch that, and it will yield the large signal parameters, no? We know how to turn this into IC or ID, no? Like no matter what, no, whether this is a MOSFET or a BJT, we know how to get IC and ID out of it, no? through the midterms, no? Through the coverage of midterms, we know how to do that. And from IC and ID, we can get the lesson from last week, no? GM, R out, R pi, no? We can get the BJT small signal models, no? From which then we can do small signal analysis.
Then you can just use slides that they styled before to be able to build your proposal by yourself.
No? So we can do small signal analysis here. Let's put that there. So we can do small signal analysis here to get the overall GM, R out, and R in of the resulting circuit. No? So itong small signal model na sinasabi natin, that's this thing. No? We talked about it in the face-to-face class. No? This is your BJT small signal model. No? And through a small signal analysis, we can turn this into yet another small signal model, but one of the overall amplifier. This is one BJT. This is for the amplifier itself. No? So this is how the small signal analysis process goes. All right? So, any questions about what we've covered so far? Okay, if not, then let's move on ahead. No? First off, let's analyze this one. No? Let's analyze the basic CE amplifier. No? So this would be V in. This V out. No? So this is your basic CE amplifier. No? I actually, sige, before this example pala, let's just store that for now. Review pala muna tayo, no? BJT small signal model. Right. So, the BJT small signal model, a BJT like this, no? A BJT like this turns into this, no? It turns into R pi, GM, VBE, right? So it turns into this small signal model, no? This is VBE and this is VCE, no? So quite frankly, we can call this the C, we can call this the B, and this the E, no? So a BJT turns into this. Ano yung formulas? How do we get these? We get these, no? Via these formulas. R pi is, well, actually, before R pi, let's go for GM, no? GM is IC over VT. And this is your large IC, no? From DC analysis, no? We also have R pi, which is beta over beta over GM, no? And R out, which is VA over IC. All right. So whenever you see a BJT in the course of small signal analysis, you turn it into an equivalent model that looks like this. No? All right. Next, we have the MOSFET. No?
For the investment that we are working on, there are also samples of products.
So the MOSFET small signal model.
So investment
Now,
is
the only difference, if you remember, is infinite yung input resistance ng MOSFET. No? Which is quite intuitive naman. No? It kind of makes sense, right? Kasi disconnected yung ground, yung gate, no? From the main circuit. No? So it shouldn't actually have an influence. No? So this is R out. This is GMV VGS. And this is just VGS. No? And this is VDS. All right? So for MOSFETs naman, GM is square root of 2K ID and R out is equal to well, actually, I think may 1 plus lambda VDS pa to, no? But lambda is usually very small. Lang, ah. Let me actually check kung kasama yan sa slides. Okay, tama. 1 plus lambda VDS is included in the formula in the slides. But for me, I tend to remember just this. All right, for R out, this is 1 over lambda ID. No? And these two are all you really need for MOSFET. No? Ito lang naman yung meron ka. All right? So I hope this one is memorable. No? I know you guys have been busy reviewing for the midterms. But this is really maikli lang naman yung module 6, no? So this is really all you needed to remember. All right? Well, not quite. No? Sige, may isa pa tayong kailangang matandaan, but we'll get into it after we start trying to get this. No? Sige. Actually, hindi pa rin pala. Ben? No? So, we know the small signal equivalents of the BJT and MOSFETs. So, now let's talk about the small signal equivalents, no, of the linear devices, no? So this is our sources and resistances, no? So, for a linear device, no? Linear device means that yung IV curve mo, no, is a line, no? So it'd be like this, could be like this, could be like that, but it's a line, no? That's your IV curve, no? So, as far as a small signal is concerned, no? The small signal model of a linear device is zoomed in, no? It's this part, but zoomed in. Kakapal yung line. But it's still the same line. No? So, in fact, no? The small signal resistance, remember, calculus, no? Calculus is basically saying, no, the essence of calculus is that everything looks the same as you zoom, ay, everything looks the same as you zoom further in. This is a line, no matter what, no? But basically, no, for any shape, no, if you zoom in far enough, it's a line, right? That's the essence of calculus, no? So we use the derivative to describe the line. This is the slope of that line, no? So linear devices are resistors, no? In small signal. And we get that by taking the slope, no? So, can anyone tell me whose IV curve is this? Anong type of device yung ganito yung IV curve? Can anyone tell me what type of device would have an IV curve that's linear? That's, well, linear with the slope.
This is a good example of dependent value, ano? Besides Eric or our team was for our device.
Yes, exactly. A resistor, no? So given a resistor R, this is its IV curve. So this is IR versus VR, no? And so if we take so this is for the resistor, no? For the resistor, this is 1 over R, no? The slope is 1 over R. And so if we take the derivative at any point, we get 1 over R, no? DI over dV is equal to 1 over R, meaning that dV over dR is R, no? So in small signal, a resistor is just a resistor of the same value, no? So resistors remain resistors in small signal is what we want to say. All right? Next, voltage source. All right. So a voltage source, let's see what it turns into. So a voltage source has an IV curve, that is like this, no? Isa lang yung possible voltage niya, no? Regardless of the current passing through it, no? So it's still a linear device. This is a line, no? But derivative of voltage versus input versus current is 0, no? So it actually turns into a short circuit in small signal, no? Voltage sources. So in fact, no? VDD turns into ground, no? Does this make sense? So bakit nagiging ground si VDD? Kung meron tayong symbol na ganito, no? What it actually implies is ganito, no? VDD relative to ground, no? So if we had VDD connecting the resistor to ground, no? Then that means this in short form. Diba? So if we turn this into a short circuit, then it's ground. no? So that's that's the reason why, no? So the VDD terminal turns into ground is the important takeaway from this. All right? Sige. Lastly, the current source. So the current source has an IV curve that has a constant current no matter what voltage it finds across itself, no? Meaning that dV over dN is infinite, no? And in fact, a current source in small signal turns into an open circuit. So that's short circuit. So voltage source turns into a short circuit. Current source turns into an open circuit. And the resistor is still a resistor. No? So those are important in our analysis. And so finally, we can start with the analysis. I was jumping the gun kanina. So now that we have this, let's make the small signal model of the entire circuit. I'm going to start with VN. So small signal model, the input turns into its small signal form. So small v, small n. Then it goes directly into the BJT. So diretso, so I will immediately write the small signal model of the BJT. So V out is connected to the collector, which is here. So I connect V out there. Emitter is grounded, so I ground it here, no? Tapos, meron tayong RL connected up here, and we have VCC, which turns into ground, as we said before, So RL turns into RL, VCC turns into ground. All right? So any questions about how we got this small signal equivalent? All right. So kung wala, ang goal naman natin ngayon, is to find the overall two-port parameters, Those are Rin, Rin, Rout, and GM, no? So sige. Can anyone tell me what the formula for Rin is? No? We discussed this in two-port networks. So what's the formula for Rin?
Can you start first with you? What is your idea for this? How, when you received the email, what did you think was going to be your next step? Whether you're actually
Pin over In given no load. No? So this is correct. Vin over In given no load. And so no load condition, I will choose to be V out equals 0. No? To keep things simple. So that's Rin. All right? So, for the others, no? V out over I out, no? And I out over V in, yung formulas. Kaso, may conditions tayo, no? So, can anyone tell me the conditions for R out and GM? Ano yung condition for R out? So, V out cannot be 0 for R out, right? And I out cannot be 0 for R out. Kasi, yun yung kinakalculate natin. For R out, that's 0 input. Tama, no? So, for 0 input, I'll just set V in equals 0 for simplicity, no? Voltages lang yung gagamitin ko. Right? Okay, sa GM, no? GM is where it gets tricky. It uses both the input and the output. So, from last week, no? What's the condition for GM?
There's a step missing first. Like, how do you reply first, or what do you do before replying even? So one thing is
No load. No? So, no load siya, meaning V out is 0 din. No? And this is how we calculate these things. All right? So, these conditions are important to remember because you will be using them to do all of the small signal analysis. No? You will be calculating this all of the time. All right? So, sige, let's proceed. No? So first, let's calculate. First, let's calculate R out. Right? So sabi natin, R out is V out over I out given that there's no input. No? So the zero input condition is actually quite simple to implement. I just put in a ground doon. No? So, anong consequence nitong ground na to? This ground puts ground on both sides of the R pi. No? So we don't care about that anymore. No? And in fact, VBE here is V in. No? VBE here is V in, but since V in is now 0, this is also gone. No? So the remaining circuit is R out and RL. No? So R out is R out parallel RL. All right? So does that make sense? This is how we calculate R out. No? Next. R in. R in is V in over I in given that given V out is ground. No? So, again, that's easy to give. No? You just put ground there. All right? So, anong consequences ng ground na yun dito sa circuit natin? Well, first off, we don't care about RL anymore. It's ground across RL. We also don't care about R out anymore. Ground across R out. No? So, the circuit becomes this. No? So, we have V in, R pi, GMV in, and ground. No? Now, to calculate R in, no? We put in I in, no? And calculate V in over I in. So, quite frankly, no? This I in is the same current as this one, no? Which is the current through R pi. And the voltage across R pi is, well, V in over R pi is equal to I in, meaning that R in is equal to R pi for this circuit. All right?
For
So that's R in.
for that, could not be
So, lastly, let's calculate GM. So, we said GM is equal to I out over V in, given that the output is 0. No?
so it's recorded
So, if the output is 0, we also have the same condition as last time. No? So, cancel din to, cancel din yon. So, really, all I need to do is copy-paste this. No? To get the equivalent circuit. But the thing this time is, the thing that we're interested in, no, is I out, no? But we know exactly what I out is now, no? I out is GM V in. It's literally that, no? So then, GM, which is I out over V in, becomes the small GM. All right?
there's maybe one possibility. For example,
So, in summary, no, we analyzed
on yes.
this amplifier,
For it, after.
and it turns out that the small signal model for it becomes R pi of the BJT, GM V in, no? And R out parallel RL, no? This is the overall small signal equivalent circuit, no? So listing out the parameters, we have R in is equal to R pi, R out is equal to R out parallel RL, and GM is equal to GM. All right? So the only thing that really changed, no, from the BJT model is the fact that the resistor is there, no? So the load resistance is there, causing us to reduce the output resistance, no? Because from the perspective of the output, no? So since this is V out and this is V in, no? From the perspective of the output, any voltage you add here, no? Kapag tinaas mo tong voltage na to, for example, right? The current increases that way and that way, no? On the downward path, on the downward path, it sees R out. On the upward path, it sees RL. No? So it's R out parallel RL is the resistance, no? That the V out is seeing from its node. No? Because when you increase it, current increases in both directions. Right? So as far as V out is concerned, it sees RL and R out. No? That's why it's R out parallel RL. Alright? Now, finally, no, we derive the gain, no, voltage gain. the voltage gain here is, well, it's defined as negative GM R out, which means that the gain for a common source, for this common source amplifier is GM R out parallel RL, no? So that's the gain for this amplifier. Okay, negative GM parallel, R out parallel RL, no? Remember, this is a inverting amplifier. It's what we called it before. And okay, so another simplification is we could argue, no? R out is typically on the order of 50K. RL is typically on the order of like 2K, no? Example values. But let's say, for example, RL was 2K, no? Then R out parallel RL would be basically 2K, no? So R out parallel RL, if R out is much bigger than RL, it means that RL wins, no? Try it on your calculator. No, if it's not already a fact to you, convince yourself of it, no? Two resistors parallel to each other, ang mananalo yung smaller one kapag if it's much smaller, no? So it turns into RL, no? So the gain for the resistor loaded common source circuit becomes GM RL. All right? So any questions? Right. If there are no questions, I will be moving on. Yeah, so let's try this, no? Ideally biased CE amplifier. Right? So the reasoning behind this is this, no? Dito sa taas, nakita natin, okay, RL is the reason why we're losing gain, no? If RL wasn't here, if RL was infinite, GMR out yung gain natin, which means that our gain increases, no? This is 50K as opposed to 2K, no? So I just need to get rid of RL. So the ideal biasing would be to use a current source, no? So spoiler alert, current sources don't actually exist, no? So it's the ideal bias, no? To our circuit. Kasi IC lang naman yung kailangan natin to get GM, to get R out, right? So for the same effect, you use a current source and you get a small signal circuit that's not loaded by the output, no? It's not crippled by the load resistance that we put because there's no load resistance. So ang small signal equivalent neto would be let me transfer this to the other node.
It's verified or
So
similar, then
we have RPi, no? So V in, we start with V in. We go through RPi. We have GM V in. This is R out. This is V out. Tapos, yung current source turns into an open circuit and then ground, no? But we don't really have to draw ground anymore, right? It's an open circuit. So it's not actually connected to the circuit. So we get this small signal equivalent, no? And anong ma-observe natin dito? This is not actually relevant, no? So ano nakuha natin? This is the small signal model. This is already the complete small signal model that we're looking for, right? So easily, Rn is R pi, R out is R out, and Gm, but big Gm is equal to Gm, no? Meaning that the overall gain, no, is equal to negative Gm R out. All right? So this is what we get for the ideal bias CE amplifier, no? We get all of the gain that is available to a single transistor, no? And we define this as A0, no? I called it AV in a lecture before because I already talked about this, no? But it's in the slides they say it's A0, and we define it, no, as the highest gain possible with a single transistor, no? It's the highest gain possible with a single transistor at this specific biasing, no? There is no way to get this higher at the same IC, no? For this same biasing. So any changes to the biasing circuit for the same IC, no? So kapag ginawa nating bago yung biasing circuit, but same yung IC na lumalabas, no? Same biasing, but different way, this can only go down, no? Because this is the best bias circuit you could possibly have kasi it leaves the raw BJT behind. Wala siyang loading, no? So this is the highest possible gain for a single transistor. And we've calculated this before, no? For the two-port networks lesson, we found that this is around 3,000, no? For an IC of like 2 milliamps, if I remember correctly, for a BJT with beta equals 70, no? So that's the ideally biased CE amplifier. Yung IC po ba na gamit dyan is yung IC if there was Rn? No. This IC is decided by the person who made the current source. No? This is the bias. So the cheat code that the current source gives you is the fact that it's a current source. Meaning you can set IC to any number that you want. No? But actually, okay. I think gets ko na yung question mo. So, yung question mo is this, do we set this IC to be, sorry, okay, mabagal na. So, do we set this IC to be the same IC as if we had the resistor in the first place? For comparison's sake, yes. No? So, if it's the same IC as if it was the resistor, no? Then this GMR out and R pi will be the same as the one that we had before, right? Because it's the same IC. Remember, these all only depend on IC. This is IC over VT, this is VA over IC, and this is beta over GM. They only depend on IC. So if the IC is the same, they have the same GMR out and R pi. No? So for comparison's sake, you would, yes, desire to make this the same IC as the one that we had earlier. No? So assuming this is the same IC as the one we had earlier, then this gain will definitely be much higher than the other one, no? By the factor of the difference of GM, of RL and R out, no? All right? Sige. So, moving on, no? Let's do some more not very ideal biasing, no? Not very ideal, but it's honest work. It's well, it's what we can actually use, no? Current sources do not exist. Period. At least the ideal one, no? We can approximate current sources, but it would look um like this. No? So parang think ganon. Tapos okay, sige, I don't want to draw it, but it has like I don't know, 6 transistors. So and that's not even ideal, no? So it's terrible, no? It's we don't use actual current sources. Anyway, yeah, no? So we have this, no? Tapos gusto ko may bias, no? Tapos may input ako. Kaso, hindi ko kayang maglagay ng DC voltage sa input ko, no? So ang gagawin ko, maglalagay ako ng resistor dito, no? I call it RB. Is the load resistor, is VCC, no? So maglalagay ako ng RB. Ngayon, the analysis goes like this, no? I'll walk you through it, no? But you guys should be able to do it by yourselves. But the thing is, okay, the reason for RB is RB generates the base current, no? What we get from RB is that the base current IB becomes VCC minus 0.7 over RB, no? Which then leads to IC being beta times this, right? So now we have a large signal IC, which depends on RB, no? So this is one convenient way to bias things, right? So now that we've done the due work, no, for the large signal analysis, no, we already have IC, no, so just drop everything once you have IC, no. Let's draw the small signal equivalent, no. So new secret, no. So parang kung naglalaro ka ng like laro right now, no, lalabas yung tutorial, no, sabihin niya new thing, no. Capacitors, for now, gawin natin siyang short circuit, no. Short circuit ang capacitor. Let's assume omega equals 0, no? Remember, capacitors are 1 over j omega c. Let's say that omega is 0, no? Or rather, maybe we can even say, let's only care about the real values for now. All right? So, since capacitors are short circuits for small signals, which they are, no? Try, no? For a high enough frequency, mag-short yan, di ba? So, we ignore that, no? Tapos may RB tayo sa taas. Tapos ground yun nasa taas, no? This thing turns into ground. All right. Tapos, we enter the transistor, no? So, we make the transistor here. That's R pi. That's GM V in. And this is R out, no? That's V out. And now we make this portion of the circuit. Well, I forgot to label V out, but that's V out. And this just becomes RL with the ground. All right? So, all right, that's how we get the small signal equivalent circuit. And this is your amplifier. This is like your real amplifier, no? Because it's the one that amplifies the small signal model. So, does anyone have any questions so far? Like about, well, how to get this small signal equivalent model? Ano lang ba yung nangyari? Nagdagdag tayo nito, nagdagdagan ng ganito. Right? That's all that really happened. Di ba? So, now, time to calculate the small signal parameters. No? The overall small signal parameters. So, let's start with Rn. No? Rn is Vin. Actually, let's start with R out. Mas clean kapag R out yung simula eh. R out is VR over I out. No? Given that Vin is 0. No? So, very quickly, we can do this. No? Ground yon, meaning tanggal to, tanggal din to. Vin is 0, so wala din to. No? So, we find that this is R out parallel RL pa din. No? Right? So, tanggal yung mga yon. We find ourselves in the situation that we had before. V out, may R out ka, tapos may RL, both connected to ground, meaning that V out over I out will be R out parallel RL. Right? Next, we have R in. No? So R in is equal to V in over I in. No? Given that V out is 0. So let's do that. So if V out is 0, then this thing cancels out, this thing cancels out. No, we don't care about that. So ano na yung bagong circuit natin? Bagong circuit natin is ito. No? Ito na yung bagong circuit natin. We have GMV in that's completely decoupled from the input part. No? So now we have an input current that way and an input current that way. No? And this thing doesn't affect it. So we can actually ignore that. No? So this is like the situation for V out. No? So for V out, pag ganon, tapos pag ganon. Right? So we actually find that R in is R pi parallel RB. No? So now, that's R out and R in. No? So lastly, we have GM. No? So GM is I out over V in. Diba? Given V out is 0. No? So, V out is 0. So we set this to ground. Again, removing these guys. No? Hindi na sila kailangan. Ground yung things around them. No? So, wala sila magagawa. So now we have this. No? And so, I out would be this current. No? Kasi it's the current that comes from V out. Diba? And V out is ground. No? So, I out yun. And we find that I out is GM V in again. Which means that big GM is actually small GM pa din. Alright? So in the end, in our analysis, no, we find the overall two-port parameters of this thing, no, of the actually let me just copy paste it na lang. So we find the overall two-port parameters of this circuit, which are now R in is RB parallel R pi, R out is R out parallel RL, and GM is still small gm. Right? Now, let me try to build up an intuition. No? Might not get it yet. No? Kaso, the more circuits you solve, no, the more circuits you see, you'll understand this perspective. No? As mentioned earlier, the V out sees the transistor on one side and RL on one side, no? So as far as V out is concerned, whenever it changes, current goes up, current goes down, and so the output resistance, no, from the perspective of the output node, which is V out, is R out parallel RL. No, those are the two resistances it sees, right? Now for this guy, it sees the input resistance of the resistor, which is the R pi, no? Input resistance of the transistor, which is R pi, and RB. Those are what it sees, no? It sees R pi and RB, no? Kaya naging ganito yung Rn natin, no? So so this type of analysis, no, is actually pretty fun to do. When you have the intuition for it na, you could look at a very large circuit and immediately be able to tell kung ano yung properties ng isang amplifier stage, no? You know where the circuit goes, you know what kind of gain the specific stage will have, or whether or not it has gain. Kung mataas yung R out niya or mababa, no? Because you could look at what the output node sees. Like, you could see that it sees a resistor, no? Or it could even see another transistor sa taas. In which case, R out parallel R out yung lalabas, no? So, ayan, these are um this is something that you could develop over time, no? But looking at the original circuit, the output that the answers that we got actually do kind of make sense, no? Is the most important part, no, that I want to impart is when we look at the original circuit, intuitively, these kind of make sense, no? When we increase R out, current flows here and here, no? When we increase V in, current flows up there and down here, no? Via superposition, by the way. Via superposition, it still works in DC, no? The analogy, the intuition still works, no? Via superposition, you turn off VCC. So tataas nga yung current if you increase V in, di ba? So yun siya, no? Right? So oops. Yung attendance is nasa Discord na, but I'll send it again here. Before I go on to the last part, no? Last part, MOSFET. Isa lang naman yung pag-uusapan natin sa MOSFET, no? So, CS amplifier, no? So, you have VDD, RL, and we have the NMOS. All right? So, we have V in and V out, no? So, based on the DC value of this, you will have a specific IC value coming out here, right? That's what we know from this amplifier. We've talked about it so many times before, no? So it should be intuitive na, no? Given a specific V in, we get a specific IC that hopefully is in saturation, no? Para may gain tayo, no? Well, more like para valid yung magandang equation, which is K over 2 VGS minus VTH squared, no? Because, I like this one way more than the linear equation, quite frankly. But yeah, this is what we like, no? So given a V in, we get a specific IC, no? And now let's take the small signal equivalent of this circuit, no? So we start with the input voltage, the fancy V in. Tapos mababangga siya dun sa gate, no? So intuitively, if you think about it, in the small signal world, kahit small signal world ka pa, the signal is going like that, but there's no current to go in. No, there's no current. There's no way your current can pass through that. It's a gap. No, there's a dielectric in the middle. So wala siya. No? And then we have GMV in again. We have R out. No? So, not even intuitively, no, this is the exact process that we're doing. We turn that into this, right? So now, let's turn everything else into what we want to turn them into. No? Ground turns into ground. V out turns into V out. Bakit? Kasi small signal yung ine-expect natin doon. No, hindi siya source. It's an output, right? Next is this part, no? Which just turns into RL and ground, right? Voila. The CS amplifier small signal equivalent. All right? And you might say, I've seen this before. Yes, you have. It's the exact same thing as before. No? It's the same. It's the exact same thing as it was for the CE amplifier. It's just that wala tayong R pi for this one. Kasi R pi is infinity for here. No? So now, since we've seen this before, redoing the analysis, no? We'll get the following. No? So R out. Ano gagawin kapag R out? We turn off V in. Right? Out, turn off in. No? So kapag turn off natin si V in, wala to. We're left with these three. Right? So R out is RL parallel small R out. Right? Next, R in. No? So R in, we need to turn off V out. No? If we turn off V out, this thing is gone. This thing is gone. And we measure I out. Uh, we don't measure I out. I'm sorry. We measure I in. No? So V in over I in here, I in is always 0. So it's infinite. No? Looking in, we see a very large resistance. So large, in fact, that we can never get a current out of it, right? Finally, GM, no? So for GM, same thing as before, V out is 0, no? And we measure the output current that's coming out, no? I out, no? So we measure the output current coming out, coming into the circuit rather, no? So from here, you measure that, no? So when you put in a tickle signal here, no, the small signal, dapat may papasok na current doon, no, which is your small signal I out. So dapat may ganun, gumaganon yung current mo, no? So that's what you get, and we find, no, that I out is again, no, equal to GMV, and what a surprise. So this is just still GM, right? Right? So now, if we talk about the gain again, this is negative GM R out. We find this is again GM R out parallel RL for this circuit, which is almost GM RL. No? It's approximately GM RL. Same as the other one, right? Only difference is, no, for BJT CE, for CE, AV would be equal to IC over VT RL. For CS, AV ended up being equal to, for basic, no? So kung resistor yung load, by the way, no? So kailangan resistor yung load for this to be true. For CS, this is square root of 2k ID RL. No? So that's the difference in their gain, right? But basically the same. No? They're the same thing, right? So, okay, finally, takeaways. No? If I had to make the best gain amplifier, like my life depended on it, I would use a BJT. Bakit? This thing depends on the root of the ID. This thing depends on IC. No? Square root of something versus that something, mas maganda ito. Di ba? Another thing is, another thing is that, no, this K is dependent on the MOSFET quality. Right? K is equal to mu naught Cox. You don't control this. The fabricator controls this. No? This is controlled by like some company, like basta, some company, no? I have few examples, no, like ST or GF, Skywater, no? TSMC, Huo, di ba? So, they're responsible for this one. Don't actually control that, no? When you pick up your transistor, done, no? Eto, you have even less control about this, no? So, what is it? Okay, what am I trying to say? For all BJTs, VT will be the same. Because this is thermal voltage. This is 26 millivolts no matter what. No? You just have to control the temperature in the room. This thing is possibly different for every MOSFET that you come across. No? So this is more stable. No? Medyo naging ano no? MOSFET trash talk session, but um ano naman advantage ng MOSFET? This is smaller. No? So people can fabricate it for cheaper and you can make a lot of them. No? So um you can compensate for this basically by using more transistors like all of the time, right? So quite frankly, I have never used a BJT after 51. Yes. No, 54 nag BJT. Sa 141 mag-encounter ulit kayo ng BJT. But basically for PCBs, no, macro scale, things that you can see the transistor of, no? So PCB, nag-solder kayo, you would be using BJTs most of the time. Kaso for yung black na chips, no, you would be using MOSFETs, no? So, yun lang, no? Yeah, so those are all the takeaways I have. And that ends our lesson for today, no? So if anyone has any questions, feel free to ask the question now. Don't forget to do the attendance, and I'll see you guys online on Friday for the next part of this session. Now we'll be analyzing emitter degenerate. All right?
Okay po, sir.
Sige. Thanks, guys, and I'll see you on Friday.